prove that the identity function y equal to x, if we find the limit as x approaches c of x is equal to c, of course, that's if you let x sub 0 be c, then as x approaches c, of course, the y value will also be equal to c. So here, f of x is our identity function x. So to prove that the limit of f of x as x approaches c is c, then we let epsilon be given, and we want to find a delta such that for all x, if the absolute value of x minus c is less than delta, this implies that the absolute value of f of x minus c is less than epsilon. But what is f of x? Well, f of x is equal to x minus, f of x is equal to x, so it's just x minus c less than epsilon. Well, this will be true, this inequality will be true if we choose delta to be equal to epsilon, or even in fact less than epsilon, it'll still work. Okay, so if suppose this is our epsilon band, okay, and then any delta that's less than epsilon is going to work. So here is your x sub 0 minus epsilon, and that's x sub 0 plus epsilon. It will still work as long as your delta would be less than or equal to epsilon, which proves that the limit of x as x approaches c is equal to c. Now the constant function, what is the limit of a constant as x approaches c? It's equal to the constant. In this case, our constant is k. But look at the function. Remember that a constant function is just a horizontal line. So for any epsilon greater than 0, we create this horizontal road strip, and take note, any value of delta around x sub 0 equal to c will guarantee that the y values, because the y values are just constant. So for any epsilon greater than 0, any delta greater than 0, such that if x minus c is less than delta, then look, our inequality will always hold, the epsilon inequality, because what is the function? K. What is the limit? K. And that's equal to 0. That will always be true because epsilon is always greater than 0. That proves that the limit of the constant function as x approaches c is equal to the constant k. Next, finding deltas algebraically for given epsilons. Okay, so for the limit of the function square root of x minus 1 as x approaches 5 is equal to 2, okay, how do we show that this is true for a specific epsilon equal to 1? Okay, our goal is to find a delta that works for epsilon equal to 1, so that for all x in this inequality, x minus the absolute value of x minus 5 is between 0 and delta, then the implication is that the f of x minus the limit value in absolute value is less than our epsilon is 1. So how do we find a delta? Alright, so we want to solve the inequality f of x minus L less than epsilon, which is this inequality. So if we solve this, we're taking the absolute value of the square root of x minus 1 minus 2 less than 1, means that removing the absolute value sign, we get the square root of x minus 1 minus 2 is between negative 1 and 1. Adding 2 throughout, we'll get now x square root of x minus 1 between 3 and 1. Then we square everything, does not change the inequality order. So then we have x minus 1. That eliminates the square root sign. So now it's between 1 and 9. Adding 1 throughout, we get x is now between 2 and 10. So what we have found by solving this inequality, we found that the open interval from 2 to 10 contains, of course, x of 0 equal to 5. Alright, so now our goal is to find a suitable delta that would place the open interval centered at 5, okay, inside this. Well, look at it this way. We have an open interval from 2 to 10. Now the distance from 5 to 10 here, of course, is 5. The distance from 2 to 5 is 3. So naturally, we pick a delta that is smaller between 2 and 5 and between 5 and 10. Okay, so if x is between 2 and 10, right? And we see here that we want our x to be between 5 minus delta and 5 plus delta. Okay, again, let's take delta 1, delta 2, set this equal to each other. We see that 2 is equal to 5 minus delta 1, and of course delta 1 is equal to 5 minus 2, which is equal to 3. And here, set this equal to each other. So 5 plus delta 2 is equal to 10. Then delta 2 is equal to 10 minus 5. Therefore, delta 2 is equal to 5. So choosing between 3 and 5, we take the smaller one. So we choose delta to be equal to 3. So if we choose delta to be equal to 3, then for all x, so that if the absolute value of x minus 5 is less than 3, then this is true, that the square root of x minus 1 minus 2 is less than 1. There's your delta and there's your epsilon. We have shown that given epsilon, so for epsilon equal to 1, we have shown that the limit of the square root of x minus 1 as x approaches 5 is equal to 2. And here is the picture. So we dictated an epsilon equal to 1 right here. And then solving the inequality f of x minus 2 less than 1, we found this open interval from 2 to 10. And then what we want to do is get a symmetric open interval around 5, and we've chosen the smaller delta, so we got this delta equal to 3, so that when we go up, the y values right here for all these x's in the blue interval from 2 to 8 will be contained in the yellow horizontal strip, which means that if they are all, the y values are here, then it satisfies this inequality.